Hello class, welcome to another video for this course. In this video, we are going to study integration by substitution. So we defined the concept of integral, the finite integral, and we introduced the um, antiderivative. We introduced the fundamental theorem of calculus and the connection between the integrand and antiderivative. And here, here is the statement of fundamental theorem of calculus. So just to refresh your mind, so suppose you have a so you know that when we studied a derivative, you know that if you have a function, right? Let's say f of x is a function, then you can take the derivative, right? If the derivative exists, then you take its derivative, right? It's and the derivative is gonna be a new function. Now, here we are doing a kind of reverse. It's like you are given the derivative, so you are given, you know the derivative, you are given the derivative, but you are looking for the original function, the function, and in this sense, we call it antiderivative, which means that, okay, if we, so if we are given the derivative, then what is the antiderivative? What was the original function that if you take the derivative gives you the this function? And the fundamental theorem of calculus says that if you are given the derivative, suppose you are given the derivative, if you take the integral of the derivative function respect to x from, I don't know, any closed interval, any closed interval, then this integral is the same as the antiderivative function at b minus antiderivative function at a. So in this way, you can see the connection between, this shows you the connection between the derivative and antiderivative in terms of integral. Okay, so we learned about this in previous discussion. We learned about the concept of antiderivative, integral, fundamental theorem of calculus. But now the next question is that, okay, so suppose we have integral. So suppose you are given a function, right, integrand, and you want to evaluate this integral, right? And so that's the question. How to evaluate integral? If we are asked to take the integral or compute this integrand, what are the techniques? What are the methods? So in this week, that's our um, focus. We want to focus on the ways to compute integrals. And we start by basic functions because, you know, we learned about derivative rules, right? So those derivative rules, if you just reverse them, gives you the rules to compute elementary derivatives. So for some basic functions, which are listed in this table, such as like constant, power function, sine, cosine, secant, cosecant, e to the x. So for a couple of, as you see in this list, when you are given a function, it is easy to, let's call them basic function, okay? Let's call this basic function. So for this basic function, it is easy to compute their antiderivative because we can use their derivative rule. Okay, so I'm gonna start with this. Let's go over these basic antiderivative, and then after that, we introduce the first technique because not, I mean, this is just a couple of functions, right? In general, we have much more complicated functions. We should have techniques to calculate those integrals. So let's start with this. So for basic functions, we are looking for what? We are looking for, in this table, we have a given function f of x. So we are given f of x, we are given a function such as constant, k as constant, and we are looking for antiderivative. And we are looking for antiderivative. Okay. So this is what we are looking for. For example, if we are given constant, what is the antiderivative of constant? So in order to figure this out, we can use basic derivative rules. For example, recall that if you had just, so here, I'm gonna do the reverse. Suppose you have function, and then you take the derivative function. So what is the function that gives me the, what is the original function that gives me constant? So this can be k times x, because we know that derivative of x respect to x is just 1. So then we end up by k. So the answer is kx. Okay. Another one. Let's go the next one. Power function, x to the n. So the question is, if you have x to the n, what is the antiderivative? So let's see. The derivative is x to the n, right? So I know that if we have a power function, recall power function rule, it should have been, a power function derivative is again a power function. The difference is in the power. So the function should have a power with one, the power in the function should be 1 more than the power in the derivative. So if the derivative have power n, the original function should have power n plus 1. Okay, so that's about the power. I know that it should have been x to the power of n plus 1, but then if you take the derivative, this is gonna give you 1 over n plus 1, right? Recall the derivative rule. If you have, if your function is x to the power of n plus 1, the derivative is n plus 1 times x to the power of n, right? It has a multiplier. The power sits as the multiplier. Okay, but here I don't have any multiplier. So that means yes, the antiderivative is x to the power of n plus 1, but the multiplier is not here, so I also need to reverse it. If it's multiplied by the multiplier here, I need to divide it. Okay, so for x to the n, the antiderivative is x to the n plus 1 over n plus 1. The next function is 1 over x. 1 over x. Okay, so if the function is 1 over x, what is the antiderivative? Okay, so 1 over x, now think about it as reverse. The derivative is 1 over x. What function gives us the derivative of 1 over x? It's natural log of x. So that's it. Natural log of x. Okay, now let's go to sine cosine function. So let's start by sine. So if the question is, if the function is sine of x, what is the antiderivative? So now let's think about it in the terms of derivative and derivative. The derivative is sine, so the function was cosine, but recall that for cosine, in terms of trig function, sine and cosine are the derivative of each other. But then if the function is cosine, the derivative is negative sine, right? That's the derivative rule. If the function is cosine, the derivative is negative sine. Okay, so the antiderivative must be cosine, and then you see here it's multiplied by -1. So here I should reverse it and multiply it by -1. Okay. The next one. What about cosine? So the question is, if you have cosine of x, what is the antiderivative? Okay, so cosine was the derivative of something. Okay, that's sine of x. That's easy because we know derivative of sine gives us cosine. So the antiderivative is just sine of x. What else? Secant tangent. Okay, secant tangent. So the question is, if we have secant tangent, what's the antiderivative? Recall that this is the derivative of secant tangent is the derivative of secant. Do you remember? Do you remember the derivative rule? The derivative of secant is secant tangent. So this is secant. And the next one is cosecant cotangent. This is the question is for cosecant cotangent. What is the antiderivative? That's cosecant. Cosecant, because we know that for cosecant, the derivative is cosecant cotangent, but with a negative sign. So here I have to say negative cosecant of x. What else? Oh, secant square, cosecant square. Okay, secant square. Secant square, what's the antiderivative? Oh, that's the derivative of tangent. Do you remember? Derivative of tangent is secant square. So that's it. The antiderivative is tangent. The original function was tangent, that its derivative is secant square. The next one is cosecant square. That is the derivative of cotangent. But for cotangent, it's negative cosecant, so this must be negative cotangent of x. And finally, we have what? E to the x, a to the x. Okay, e to the x is easy. Why? Because look, remember that e to the x is a function that its derivative is itself, right? So if you take the first derivative, second derivative, any derivative, it always is the same. So antiderivative is also the same. But a to the x, what's the antiderivative of a to the x? Okay, a to the x, if you take the derivative of a to the x, okay, so suppose your function is a to the x and take the derivative, it's gonna be natural log of a times a to the x. So if you're looking for the antiderivative of a to the x, yes, it is a to the x, but then the derivative, this is the derivative, does not contain the natural log of a. So it was reversed, which means that if it's multiplied by natural log of a, now it should be divided by natural log of a. Okay. And what's the next one? 1 over 1 plus x squared. 1 over 1 plus x squared. The antiderivative is, so this is the derivative of arc sine. Do you remember arc sine or sine inverse? Derivative is 1 plus, so sine inverse, the inverse function of sine, or arc sine, the derivative is 1 plus x squared. So the antiderivative is sine inverse. And the last one, 1 over square root of 1 minus x squared. So this is the derivative of arctangent. Do you remember? Arctangent, arctangent, or tangent inverse, any notation that you like. The inverse of tangent function. Derivative is this, so this is going to be tangent inverse. So as you can see here, we just use the derivative rules in order to get some formulas for basic function for antiderivative, right? So it's like in the table on the right, we are given the function. The question is, what is the antiderivative of the function? And we just look at the derivative rule, try to reverse it in order to come up with a formula for antiderivative. It is good to remember these antiderivative, as we are going to use them a lot in taking derivative. Okay, so if you have a question like this, you are going to take the integral of this function and look for this function. Okay, so you want to take the integral. That means you need to find the antiderivative. But look at the type of function. This is a power function. Okay, we have a formula for power function. This is a square root. Okay, a square root is also a power function. We have a formula, and this is exponential. 5 to the x is exponential. We have a formula for antiderivative for exponential as well. So that means for a question like this, because it's a combination, it's a summation of basic function, I can just use this table in order to evaluate this integral. So I'm going to show you this example. So it's the integral. So the question is the integral of the question is the integral of, I think, x cube. It's x cube minus a square root of x plus 5 to the x. So we are looking for the integral of this function respect to x, respect to variable x, from 0 to 1. That's the question. Okay, so you want to evaluate this because this is a combination of basic function. We can apply the antiderivative rule. So this is a power function, right? So by antiderivative rule, the derivative is going to be x to the 4 over 4. If you want, I can recall what I'm using in this step. Okay, so I'm using this one. Okay, you have function, its antiderivative, right? Okay, so the first one is power function. So you have x to the n. The antiderivative is x to the n plus 1 over n plus 1. So that's why here, this is going to be x to the 3 plus 1 is 4, x to the 4 over 4, okay? Minus a square root of x. A square root of x is the same as x to the power of half. So treat it the same way. It's a power function. The power is half. So by antiderivative formula, it's going to be half plus 1 over half plus 1, right? Plus, and then 5x. So this is an exponential function, a to the x, a to the x. And the formula for this was a to the x, but with the reverse of natural log of, divided by natural log of a. So this is going to be 1 over natural log of 5 times 5 to the x. Okay, so this is it. This is the antiderivative function, and then we need to evaluate it from 0 to 1. So let's see. The rest is simplifying. That's it. I mean, just in this line, we calculated the antiderivative. The rest is just computation and simplifying. Okay, so I'm going to simplify this one more step. So this is x to the 4 over 4 minus, this is going to be x to the 3 over 2 . Okay, that's it. From 0 to 1, right? Okay, now, first we substitute the upper limit, which is 1. So it's going to be, so first we substitute 1. Recall that this is going to be f of 1 minus f of 0. And this is your f. This is your antiderivative function. So evaluated at 1, it's going to be 1 to the 4 over 4 minus 1. Just substitute 1 into the function. Okay, so this is gonna be f of 1 minus f of 0. So this is gonna be 0, 0, 5 to the 0. Okay? So this is gonna be 1/4 minus, this is gonna be 2/3 plus 5 over natural log of 5. Okay, and minus 0, 0, and this is gonna be 1 over natural log of 5. So 1/4 minus 2/3 plus 5 minus 1, 4 natural log of 5. If you want to simplify further, you can use a calculator. But that's the idea. The idea is that you use the basic rules. You use the antiderivative rules for basic function in order to find this integral. And then you just evaluate it at the given limits. And if you want to see the final, I didn't use a oh, your textbook also leave it as natural log of 5. Yeah, so after simplifying, it's 4. So it's gonna be negative 5 over 12, that's right, plus 4 over natural log of 5. Okay, so that was not too bad, right? Because if you learned about derivative and derivative rules, this is just doing the reverse, and by a little practice, you should be able to calculate integrals such as this. But sometimes the integral could be a little more tricky. And that's the case when that is the case like when we introduced chain rule for derivative. Do you remember? There were times that, I mean, sometimes your function, for example, sometimes, so I'm talking about derivative, right? Not integral at now. So sometimes when you take the derivative, recall that, for example, you have this function, sine of x. You take the derivative, you say the derivative is cosine of x, right? So this is a basic function. The function is sine. You just use the derivative rule and then you say that the derivative is cosine. But if you remember, sometimes the function was more complicated. For example, it was sine of 5x plus 2. And we couldn't just simply say, okay, this is sine, so derivative is cosine. No, if you remember, because this was because the function is no longer a basic function, this function is a composition function. So it's like you have two functions, the outer function, which is sine function. So this is the outer function, which is a sine function. And then there is a inner function, which is in this case a linear function. So in these cases that you had a composition of two function or three function or more function, then there would be a concept of, okay, this is the inner function, this is the outer function, and then how to take the derivative of such composition. If you remember, we introduced the chain rule. Do you remember? The chain rule. And we said that, okay, so whenever you have composition, the derivative is going to be the derivative of inner function, which is in this case 5 times by, now the derivative of outer function, okay, for sine is cosine in terms of the inner function, or in general. So you see, in this case, there is a difference between the calculation on the left and right. On the left, you have the function sine. It's basic, so you can easily say the derivative is cosine. But on the right, you have a more complicated function. It's a composition of two functions. And then there needs to be a technique, in this case, chain rule, in order to do that. So just recall, I just want to refresh your mind of what was chain rule. In chain rule, you have a function that is a composition of two functions. So for example, you have f of u of x. So f is a function, u is function, and this is a composition of those two. Then the derivative is the derivative of inner function. So in this case, inner function is u of x. So you take the derivative of inner function and then multiply it by, now you take the derivative of outer function at the inner function. So that's the chain rule, that when you have a composition, you take the derivative like this. Okay, so we have the similar case for integral, that sometimes the integrand is a composition. And then what we actually do is reversing the chain rule. Because you see, it's like sometimes this is given. I mean, like here, suppose you have something like this. The question tells you, what is the integral of 5 times cosine of 5x plus 2 respect to x? So it's like, now this derivative is given. The question is, what is the antiderivative? And you just saw that with chain rule, I showed you that this is the antiderivative of sine of 5x plus 2. You see, so we are looking at the cases that you have the integral of, like the chain rule, u prime of x, f prime of u of x. And then, okay, you need to figure what was the antiderivative. So it's just reversing the chain rule. Now you are given this and you need to figure the original function, okay? So, that means in these cases, we need to determine the general antiderivative of a function such as this, you see? So that's the thing. So because look at the, so just look at the table one more time. It's because using that table, the basic function, using this table, we can say what is the antiderivative for these basic functions, such as x to the n. You are given x to the 5th. You say the antiderivative is x to the 6th over 6. So if the function is one of these basic functions, you can just figure the antiderivative using this table. But if you have a function like this, 5x minus 3 to the power of 6. So see the difference. I mean, the function is 5x minus 3 to the power of 6. And the question is, what is the antiderivative? What is the integral? Okay, if this was x to the 6, then I could say this is a power function, so antiderivative is x to the 7 over 7. But this is not simply x to the 6. There is an inner function, which is 5x minus 3. So instead of x, I have 5x minus 3 to the power of 6. So that reminds me of, again, composition. It's a composition of linear function and power function. So this is the case we need to reverse the chain rule. So what to do in these cases when we have the integrand is like a composition function? So what we need to do is just reversing it's just reversing the chain rule. I'm gonna, your textbook describes it in some way, and I would like to describe it in my own way, the way that I think is easier to get to it. So I'm gonna show you this question. So suppose you are looking for the integral of 5x. So the same example. So suppose you're looking for the integral of 5x minus 3 to the power of 6 respect to x. when we say the integral of this function, that means the antiderivative is just a different wording, right? So you may say, like, I think in your textbook says, determine the general antiderivative, right? What is the antiderivative of 5x minus 3 to the power of x? Which is the same as saying what is the integral of this function respect to x. Okay, so think about inner function and outer function one more time. This is a composition, right? You have, so first of all, this is a power function. You see that because you have 5x minus 3 to the power of 3. So there is a composition of power function. And then this, since this is not only x to the power of 6, it is 5x minus 3. It is 5x minus 3, right? It's a 5x minus 3, which is a linear function. So there is a linear function as well. And in this case, the power function is the outer function. This is the outer function. And the inner function is the linear function. Now, what is the technique? So here the technique, which is called U substitution, is that take the inner function. So, I mean, whenever you get a question like this, try to identify which one is inner function, which one is outer function. Then take that inner function and label it. Label it, I mean, it doesn't matter what letter you use, but we usually use U because this is called U substitution. And we label this inner function with U, okay? So we just label it. So instead of this, we call it U. So rewrite it, rewrite this integral. So this is gonna be the integral of U to the power of 6 dx, okay? So we just label the inner function. Okay, what do we have now? Now we have an integral in terms of U, but then it should be, the integral should be taken respect to variable x. But when I look at this, look, my point is that here, this is very nice. U to the 6 is very nice because U to the 6 is a power function, right? I know how, I know that this is going to be, the antiderivative is going to be U to the 7 over 7. That's easy, right? But the problem is that we are not taking here, the integral is respect to x, but here the variable is U. So let's figure, the idea is that to rewrite everything in terms of the variable U. For that reason, we need to rewrite dx in terms of variable U and see how we do that. Okay, we named 5x minus 3 as U. Now take a derivative from both sides, which means that take the derivative of the left respect to variable U, because we have two variables, U and X. So take the derivative of left respect to U, take the derivative of right respect to X. So derivative of 5x minus 3 respect to X is 5. And denote that we are taking the derivative respect to X. Why? Because in this equation, we have two variables, U and X. So when you're saying I'm taking the derivative, you should mention that this is the derivative respect to which variable, okay? Now, we are looking to rewrite d of x. And here we have the opportunity to do that, because here I can express d of x in terms of d of u. If you divide both sides by 5, then you can say that dx is, you can express it in terms of u. So then your integral is going to be u to the 6 times, what is dx? Dx is 1/5 of du. Very nice. Look, now we have 1/5 integral of u to the 6 du. This is very nice. This is one of the basic, I mean, at this step, we reached a basic integral, basic function. This is a power function, and we are taking the integral of u to the x respect to u. So now you can apply the antiderivative rule for power function. So this is gonna be, because it is u to the 6, it's gonna be u to the 7 over 7. And that's it. So the answer is 1. 5 times 7 is 35, u to the 7. But because originally we started with variable x, right? The question is in terms of x, 5x minus 3. So we need to give the answer in terms of x. So now substitute u in terms of x, which is 5x minus 3. And that's the final answer. This technique is called u substitution. Okay, so any time that the integrand is a composition of multiple function or two function, we can use one technique to do is u substitution. And again, the technique is this way. You take the inner function and label it with u. And then try to rewrite the whole integral in terms of this new variable u. Then it becomes something easy, something basic to take integral. Take that integral and then substitute the original u in terms of x for that question. So that's the u substitution. I'm gonna, I think, you know, I think for in general, whether u substitution or other techniques for integral, it just requires practice and practice, and you should see a lot of examples. So I try to give you more examples of u substitution so that you get the idea. For example, look at the activity 5.3.2, and I'm going to show you the first one, sine of, so the question is, what is the integral? So this is the activity. And part A says find the integral of sine of 8 minus 3x, 8 minus 3x dx. Okay, so whether the question says find the integral or says antiderivative, they are the same, which means that think about sine of 8 minus 3x as the derivative. What was the antiderivative of this function? Okay, if this was just sine, I would say cosine, but it is not just sine of x, it's sine of 8 minus 3x. So there is an inner function, you see? So this is the sine is the outer function, 8 minus 3x is the inner function. So here I have a composition of two functions, composition of a trig function and linear function. So that means we need to use u substitution. What should be the u? The inner function. So let u to be 8 minus 3x. And then take the derivative of both sides. So du is going to be negative 3 dx. Now, express or rewrite your integral in terms of u. So instead of variable x, everything should be in terms of u. So it's going to be sine of u, because 8 minus 3x is u, and then dx. Okay, let's solve it for dx. How can I express dx? Maybe I use another color. I need to, from here, I need to solve it for x, dx. dx is negative 1/3 of du. Do you see that? From this equation, we can solve it for dx. So dx is negative 1/3 du. Very nice. Now, look, I have the integral of sine of u du. So now this is a basic function, sine function. What is the integral of sine? It's negative cosine. So it's going to be negative cosine. So it's going to be 1/3 cosine of u. Okay, because the question is in terms of x, we need to give the answer in terms of x as well. So now substitute back. U in terms of x is 8 minus 3x. That's it. Got it? Let's see another question. B, secant square of 4x. Okay. B, secant square of 4x dx. Okay, so again, here I have secant function, that's a trig function, and I have 4x, which is a linear function. So we have, and they are composed. So this is again a composition. This is secant is the outer function, and then 4x is the inner function. So we need to reverse the chain rule or use u substitution. So take u to be the inner function, and then take the derivative. Derivative of u is 4 times derivative of x. Then express everything in terms of u. So this is going to be secant square of u. And then now we need to express d of x in terms of u. dx is going to be 1/4 du. If you divide both sides by 4, it's going to give you 1/4 d of u. Now we have an integral that is entirely in terms of the variable u. Okay, now we have a basic integral, secant square. What is the antiderivative of secant square? It's tangent. It's tangent. Tangent of u. Okay, you want to express your answer in terms of x. U is 4x. Okay. So u substitution, maybe I show you D, maybe I show you more. For example, look at this one. Cosecant, maybe I also show you C. Let's first see, look at C. C, because it's, I think when we do integral, techniques of integral, it's all about practice and practice. You should see many examples. Integral of 1/11x minus 9 dx. Okay, so this is also none of the basic function that I can immediately say what is the antiderivative. And this is a composition, but what type of composition? So it's 1 over something, right? So it's 1 over something. So it's a composition of 1 over x, not the variable x, I mean 1 over something. And inner function is a linear function, composition of this and 11x minus 9. So this is the outer function, and this is the inner function, right? So use substitution. Take the inner function as u. So we say let u to be the inner function. Take the derivative of both sides. And then just rewrite everything in terms of u. So it's going to be 1 over u, and then dx is going to be what? 1/11, divide both sides by 11, du. So 1/11 du. Very good. But now I have 1/11 Integral of 1 over u du. So this is a basic function. This is in the table. This is one of the basic function. The integral of 1 over u is ln of u. That's it. 1 over 11, ln of, what was u? U is 11 x minus 9. That's it. Okay. So I may leave the rest for you to practice, but they are all the same. It's a composition of inner and outer function. So if you just use the u substitution for these functions, just the first thing you need to recognize is that these are composition of two functions, and just you need to identify which one is the outer function, which one is inner function. Then you want to use the u substitution technique. Take the inner function as u, and then take the derivative, express everything in terms of u, and then take the integral. Okay, now let me show you a couple of examples that are a bit different, because here, I mean, in these examples, it's just you take the inner function as the u, take the derivative, and then it's straightforward. It could be, there could be examples that need a bit more work. For example, like this one. Example 5, 3.2. Evaluate this integral. Okay, so I'm going to show you this one. So this is the integral of x cubed. So this is example 2. The integral of x cubed multiplied by sine of, what is the inner function here? 7x to the 4 plus 3. Okay, dx. Okay, so here it seems a bit different than the previous examples, because I mean, it's not just sine of something, it is also multiplied by x cubed. But the idea is the same. Just think about this the same, that there is a composition here. I know that it's also multiplied by x cubed, but think about here that there is a composition of sine, which is the outer function, and then this linear function, which is the inner function, and go by u substitution, regardless of the fact that this function, this sine function, is multiplied by x cubed. You go by the same way. Take the inner function and name it as u. Label it as u. Then take the derivative. So derivative respect to u, and take the derivative of the right side respect to x. 7 times 4, 28, x cube dx. Okay. Okay, so now let's express, so the technique is the same, just use substitution. Now express everything in terms of u. So it's gonna be sine of, so look, we have, what do we have here? X cubed times sine of u times dx. Okay, the part of sine of u is in terms of u, but the part that it has x cubed and dx, it's still in terms of x, and that's not good. We need to rewrite x cubed and dx in terms of u. So, but it's not difficult to do that. Look, because we have it right here. Here, you can see the term x cubed times dx. So from this equation, you can rewrite it in terms of u. X cubed times dx is 1 over 28 d of u. So now I'm gonna say this is sine of u times x cubed dx is 1 over 28 times du. Very nice. Now we have an integral that is entirely in terms of u. Integral of sine, which is cosine. It's cosine of u. Sorry, it's negative cosine. So it's going to be negative 1 over 28 cosine of, now expressed it in terms of x. U is 7x to the 4 plus 3. Okay, so pay attention that there is nothing new. The example is a bit more complicated, but the technique is the same. The technique is u substitution. The fact is that the integrand is a composition of, contains a composition of two functions, but the technique is the same. We take the inner function, label it as u, we take the derivative, and then we just rewrite the whole thing in terms of variable u. And then we take the integral or antiderivative. Okay, let me show you one more example. If you want to check the solution, you can also look at the solution of the textbook as well. But the answer is negative 1 over 28 cosine of 7x to the 4 plus 3 plus c. And plus c is just a constant. We add this constant because, you know, when you take the antiderivative, it can be with any constant. So we always add c to the antiderivative. If it is not, if there are limits of the integral, there is no need for that. But because this is indefinite, then there is a need for that. Okay, what else? Let's see another example. Oh, what about this one? X times e to the x. Let me show you this one, this example. The integral of x times e to the x squared dx, right? X times e to the x squared dx. Okay, that's the question. Okay, so what do we see here? It is x multiplied by another function, but that function, pay attention to the function, it's e to something, right? So that's the outer function. And then the inner function is x squared. So this is the inner function because it is e to the something. So my point is that when you see the e to some power, that's an exponential function, right? So the function, I mean, this function is exponential function, but inside the variable is x squared. X squared is power function. So this is the inner function in this case. So we take the inner function and we name it as u. Then take the derivative of both sides, 2x times x. Now you are ready to express everything in terms of u. So we have x multiplied by e to the u, right? X squared is u. Okay. What is left is x and dx, x times dx. But that is also easy to express, to be expressed as u, because we have it right here. From here, we can solve it for x dx in terms of u. So it's going to be half of du. So it's going to be, so the integral is going to be e to the u times half of du. Then it is easy to take this integral. The integral of e to the u respect to u is e to the u. Remember? It's just e to the u. And now you wanted to have the answer in terms of x. So it's going to be x squared. That's it. So that's the solution for this integral. Okay. And now let's look at another example. So look at this activity. Maybe I show you one of the integral in this activity. For example, let's look at this one, the second one, e to the x times sine of e to the x. Okay, B. So in this activity, look at part B. The integral of e to the x sine of e to the x dx, right? Okay, so again, here we have e to the x multiplied by sine. I mean, try to understand what's happening here. We have e to the x, that's an exponential function, multiplied by sine function, that's a trig function. So here we have exponential function, and here we have a trig function. But our trig function is not just a basic one like sine of x, it's sine of e to the x. So in this, here we have a composition. That's why we use substitution, because sine is not simply sine of x, it's sine of e to the x. So there is an inner function and outer function here. And in this case, the inner function is e to the x. And that's why we take e to the x as u, and then we take the derivative. Okay, so then now let's express everything in terms of u. So e to the x, look, we have sine of u, and then dx du, look, because we have e to the x times dx. E to the x dx is just simply du. Very easy. So integral of sine, which is cosine of u, which is negative cosine of u. So it's going to be negative cosine of e to the x. Oh, let me show you this one. Maybe I show you all of it. Let me show you A as well. First A. 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 Okay, so let me show you this example. So we have x squared over 5x cubed plus 1. So we have the integral of x squared over 5x cubed plus 1 dx, right? And we want to compute this integral. Okay, so this is a fraction, right? It has numerator and denominator. And so we have, you know, sometimes it's easy to think about this as to think about a function as an inner and outer function, as a composition of two functions, and then take the inner function as the u. And some cases, if like this, it's not super obvious to see how is the composition. I would recommend thinking about this. What is the function that if you take it as u? Because what does u substitution says? It says that take one of the function, which is inner function, as u, and then label that function as u, and then that would, if you take the derivative of that term, then it would help you to rewrite everything in terms of u. So it's like getting rid of the variable x. So in this case, we have two options. Either we can consider x squared as the u, or either numerator or denominator. You can either name numerator as u or denominator as u. But look, if you take the numerator as u, then the derivative is going to be 2x dx. So then what's going to be? It's going to be u. And then, yes, you can also express d of x as half of, yeah. So you see, so the problem is that if you take the numerator as u, then what do you want to do with the denominator? How do you want to express the denominator as u? So it seems like taking the numerator as u, it's not gonna be helpful. But what if we take the denominator 5x cubed plus 1 as u? Then look at it. The derivative is gonna be 15x squared times dx. And why this is gonna be helpful? The reason is that the derivative contains the numerator. You see that? So the idea is that usually you take the function as the u in a way that when you take its derivative, that derivative appears somewhere in the integrand. You see that? So that helps you to express everything in terms of u. So now we can say that, look, we can say that dx, I'm gonna solve it from here. Look, x squared dx is 1 over 15 du, right? So I can say the numerator is 1 over 15 du, and then denominator is u, right? So instead of, look, x squared dx, x squared dx is 1 over 15 du, and then the denominator is just u. Then you see now we have, in this way, we have everything. We have an integral that is expressed as one variable, just variable u, no more x. And now this is one of the basic function, 1 over u. What is the derivative? What is the antiderivative of 1 over u? It's natural log of u. So the final answer is natural log of 5x cubed plus 1. Okay? So, and yeah, I think we can do the last one. I leave it as for you. It's not too difficult to see what should be u and what should be the so we went over the u substitution evaluating integral, and I mean we are done, but I just want to show you one of the definite integral using u substitution so that you see that the technique is just the same, and you just so let me show you one example like this one, x e to the x. So the question is, evaluate this definite integral. The integral is x times e to the x squared dx from 2 to 5. Okay, so x times e to the x squared from 2 to 5. That's the question. Okay, so here we need to use u substitution. Why? Because e to the x squared is the inner function. So the technique is that you take the inner function x squared as u, and then you take the derivative of both sides, left respect to u, right respect to x. And then we try to express everything in terms of u. And I'm gonna forget about the limit for now. I mean, my technique is that maybe your textbook do it in another steps, but my way is that I think about it as an integral without limits, and at the end I will substitute that limit. So look, the first step is I'm gonna rewrite everything in terms of u. So e to the x squared is gonna be e to the u, right? And then look at this item. X, we have x times dx, right? And I have it right here. X times dx in terms of u is half of u. Half of u is x dx. So I'm gonna write half of du. In this way, we rewrote everything in terms of u. Now take the integral. the integral of e to the u, which is going to be half of e to the u. Now it's going to be half of e to the, what is u? U is x squared. Okay, now that you are done with the taking integral, just substitute when you have everything in terms of x, right? Because your original integral is given in terms of x, and this means x from 2 to x from 2 to 5. So when you have your answers in terms of x, substitute just this value of 2 and 5 to evaluate this definite integral. So this is gonna be half of e to the 5 squared minus half of e to the 2 squared. So it's going to be half of e to the 25 minus half of e to the 4. If you want, you can also use a calculator to simplify it. Yeah, you see, half of e to the 25 minus half of e to the 24. So your textbook here is like me. It takes the integral, and then when you have the answer in terms of x, it substitute the upper and lower limit. So that's it. So you see, it's nothing difficult. Just when you have a definite integral, you forget about the limit of integral for a moment, just compute the integral. Once you have the answer in terms of x, then substitute the limit into the answer in order to find the solution. So that's all about u substitution. Now you can practice this. I encourage you to practice these exercises. These are good questions, and in all of these exercises you need to apply u substitution in order to evaluate these integrals. Thank you for watching this video. I'll see you in the next one.